Well, I'll say good morning to everyone. So, how many of you like Chinese food? I love Chinese food. And I haven't had good Chinese food for a month. So I decided to go get some this week. So that's my way of saying I won't be here on Thursday and again next Tuesday. But don't worry, I'm going to record the classes ahead of time. In fact, I'm going to record them this afternoon beginning at 2 o'clock in the other room. If any of you are available, you can come there. If not, you can come to class here next Thursday this week and Tuesday next week, and the classes will be shown here. Or I guess you can watch it on your computer. But it must be much more fun to come to this classroom and watch it. But it's up to you. Either 2 o'clock today, 2 o'clock until midnight or something. I guess I have to record 2 classes. 2 o'clock, or come to your regular class on Thursday and then again next Tuesday. Okay, so last class, we were talking about the Twyman Green interferometer. And if I remember right, right at the end of class, we said that if we look at this interferometer, we have light, coming out down here, where we normally see the interference pattern. But we also have light going back towards the source. And we said that if this were a dielectric beam splitter, so there's no absorption, then the pattern going back to the source here is 180 degrees out of phase with the pattern out here, the interference pattern. So they're complements one another. So if we were to adjust this interferometer to have one big fringe down here, then all the light's going back here. And we can very easily see that by putting in a beam splitter here and looking at the light reflected out. If this is not a dielectric beam splitter, but if it has a metallic coating, and so it can absorb some of the light, and with a metallic coating, the phase change on reflection can be, who knows what, it can be anything. And so the output down here and the output back here may not be complements of one another. In fact, they might even be in phase. They could be dark together or they could be bright together. And to see where the light's gone now, you have to look at this beam splitter and take into account that some of the light will be absorbed at the beam splitter. And so you really have to add up the amount of light down here, the amount of light going back to the laser, and the amount of light absorbed by the beam splitter to get to all the light going into the system. That's assuming both these are high reflectivities, 100% reflectivities. Having this light going back towards the laser can be a problem, can be a practical problem. Have any of you fed light back into a laser? And what happened?
It's really strange, it's transient.
It becomes unstable, it may begin pulsing. In any case, it's very, very bad behavior. And so if that's going to be a problem for you, some way you need to stop the light from getting back into the laser. And you could just tip and tilt things a little bit so it doesn't go right back to the laser. But sometimes you're testing things. We haven't talked about corner cubes yet, but that's be a case when you're testing a corner cube and the light goes right back on itself and it feeds right back into the laser. And so a bad problem. And so what we do, I hate to go to the blackboard, but well, the whiteboard, I guess it is. But what we will do is a little optical isolator. And there's different ways of doing that. But the way that I have done many times, so here's our laser, the light coming out, put in a polarizer here. And then we put in a quarter wave plate. And then it goes out here to our So if we go through the quarter wave plate, what's the state of polarization after coming out of the quarter wave plate? Well, general, it's elliptical. And how do I make it circular? And put the axes at 45 degrees to the direction of polarization. That will make it circular. So light goes out and comes back through the quarter wave plate again. And so the quarter wave plate's going through it twice. It's going to act like a half wave plate. And the half wave plate will rotate the direction of polarization. And it's going to rotate the direction, twice the angle between the axis and the direction of polarization. And so if we put it in at 45 degrees, it will rotate the direction of polarization 90 degrees. And so it will not go back through the polarizer. So that will stop you from feeding the light back into the polarizer, or into the laser, I mean. It's not going to go through the polarizer, so it won't go back into the laser. Now the other kind of practical thing, when you mount this quarter wave plate and polarizer, you don't want to mount it just so it sends light. You don't want the beam to be normal to it, because that's going to feed back into the laser. So you want to tilt it just a little bit. So sometimes we have to use an optical isolator. Often we don't, but sometimes we do. Now we said when we aligned this system, I think we said this, that we will look down at the focus of this lens, and the two beams will come to focus, and you're going to see two spots. And so you'll simply align one spot on top of the other one, and you'll see the fringes here. And then you can tip and tilt to get the right number of fringes. We put in this little stop here. We said one reason was that this beam splitter has a second surface, and we often have a beam splitter with some wedge in it. And so the light reflecting off the second surface will leave at a different angle. And so this small aperture here, then the light will come to focus off to the edge, and it won't get to the interferogram. But even besides that, it's nice to have a small aperture, just kind of cleaning up. You don't want to make it too small, because that will remove all the aberrations from the beams. But it depends on the focal length of the lens and whatever, but typically maybe a millimeter or so in diameter. And other strays in the system then will be stopped by this. Let's see, what else do I have I want to mention here? Vibration is can be a problem. In fact, we have a whole section in the course where we talk about phase shifting interferometers that are not going to be sensitive to the vibration, or not so sensitive anyway. But right at this point, I'll just mention one thing, that if you set this up and you have some vibration, this is a very simple thing, but sometimes if I just put a ruler or a meter stick, lie it on top of the mirror on top of the beam splitter, or just more coupling, and you'll be amazed at how much that often will reduce the vibration that you see. Just a little coupling here will make a lot of difference. I think that's about everything I was going to say at this point. So any questions before we go on to the next slide? We like to have a clean interferogram, and with a laser source, any reflections will give you interference fringes that you don't want. And so some way we like to maybe reduce the coherence a little bit. And one technique that people use, is maybe too many words here, but I'll say what's on that, is that we take our beam of light. This is coming from the laser now. This will be the source. The light's coming from the laser, and we're going to put in a rotating piece of ground glass right here. And we're going to have some distance between the source point here and the ground glass, so the source will have some diameter. And then we're going to rotate this. And so that's going to reduce the spatial coherence of the source. And that will tend to clean up the interferogram. If you make this too large, then you're going to lose fringe contrast. And so what is too large? Well, if I go back here, if these paths are really matched, sort of like going back to the Fizeau interferometer we talked about in the class before, you can use almost any source. It's only when these two paths differ in length do we worry about both temporal coherence and spatial coherence. And if I think here for a second, if I have an extended source back here, which I created, in this case, by illuminating a rotating piece of ground glass, so the source has some size here, and I put in a collimating optics to collimate the light. I'm going to collimate the light, so I'll collimate the light coming from each point making up the source, but because I have an extended source, it's going to be collimated waves at different angles in the cavity here. And if I move this mirror out here some distance, so let's say that the path lengths here differ by d. If the light's going through here at different angles theta, remember back from 505 that we're going to see an OPD for the different thetas that goes as what? 2d cosine theta. And so if d is 0, as I pretty much have in my drawing here, then we don't have this path difference due to the different angles. But if I move the mirror out here some distance, I will have a d, and so I'm going to have an OPD that's different for the different thetas, and so that's going to reduce the fringe contrast. And so the larger the d is, the smaller the source has to be, so you have to keep theta smaller. And so there's no real number that I want to say on just how large that source is. You kind of have to play with it a little bit. But you don't have to extend it too much in order to see that you're going to kind of clean up the interference pattern a little bit. Now, why do I have to rotate this ground glass? Why not just put the ground glass in there? That would be an extended source. But then what? All the points are coherent with respect to one another, and I'm going to see a speckle pattern. And so I want to rotate this to get rid of the speckle pattern. Rotating it, I mean, I hate mechanical things. I hate moving things, especially in interferometer, moving parts, vibration. And so this is easy to put on paper, but it's harder to make in practice to have something that's rotating and it's not vibrating at the same time. Anyway, some interferometers use this, or maybe they'll just use a fiber and they'll move the end of the fiber around or something. But it's nice to have a little bit of an extended source there that will clean up the image a little bit. Now, the next thing is, if I go back here, I'm forming an interferogram. And I'm probably putting a CCD array here nowadays. I should also mention this. A CCD array has a window on it. Window, reflections, probably the window is coated, but it's probably not a great coating for the particular wavelength they're using. And so you can often get stray or spurious interference fringes from the reflections off that window. And so how do I get around that problem? Well, one approach is you take the window off. I mean, this is a real practical problem. If you're selling interferometers, I mean, you can't have all these stray interference fringes. People aren't going to buy your stuff. So one approach is to take that window off. What's bad about that? Yeah, you get dust on it. You can touch it with your finger, and you can very easily kill the detector. So that's not too good of an approach. Another approach is you can put a wedge on this window. Or maybe you can buy CCDs with wedge in the window, special made to order. And of course you pay a lot of money for those. And being James C. Wyant, I don't like that. So the other approach is you can index match a wedge to the window. And so you still get reflections, but hopefully the reflections, the angles are large enough you won't see the fringes. Well, the other thing, what I was going to say here is that you may want your image to fill your detector. And if I'm testing a large mirror here, okay, it fills the detector. Now, next mirror I test is one half that size. So now I'm only using half of the detector. And so people like to not just have an imaging lens here, but they like to put a zoom lens in here. So let's talk about that for a second. So we might put in here's our image formed in space, and between that and the detector, we'll put in a zoom lens. And so we can change the size of the image to always fill the size of the detector. And I guess you could make a special zoom lens and put on real high quality air coatings to get rid of reflections, and people do this. But again, that's a lot of money. And so you'd like to just use some commercial zoom lens if possible to make it less expensive. And stray reflections, stray interference fringes drive us crazy. So the other approach that people have used is to put a ground glass here. So the image from your interferometer is on this ground glass, and then my zoom lens simply relays this image to my detector. So the ground glass is causing the light to go at many different angles, and I'll still get these reflections and spurious fringes, but they're going to tend to wash out because the light's going through at many different angles. All these stray reflections are incoherent if I rotate the ground glass anyway, and I'm going to get a nice clean image here. So this has been a common thing for many years. Couple problems. One is the ground glass, you're rotating it to get rid of speckle, moving parts again. And to rotate a piece of ground glass without introducing any vibration is not as easy as it sounds. So that's a problem. The other problem is the ground glass is going to cause a large amount of loss of light in the system because of all the scattering. And so I'll probably need a little more powerful laser to work here. Now I think, for maybe 10 years or so, I've been saying you really don't need zoom lenses in interferometers. And I don't know if I was right 10 years ago or not, but I think I'm right today for sure. Because nowadays you have detectors, you have so many pixels. You have a 1,000 by 1,000 element or 2,000 by 2,000 element detectors. They have a million, maybe 4 million, maybe 6 million detector points. And so it's no longer so essential to fill the entire detector. And you can do And if you want to see a larger image, you just blow it up in the software, and you have enough detector points. And I think my feeling now is that this zoom lens and rotating ground glass and all that causes more problems than what it's worth, and just use a large, a detector with a lot of pixels, and even if you're only using a quarter of the whole array, you still have a lot of pixels, a lot of data points. So I think that's in my opinion, that's a better approach nowadays. The other thing people are been so careless about over the years, and it didn't used to make much difference because you didn't have a lot of pixels here, but people did not do a great job of imaging here. And so you may have 1 million pixels, but your resolution makes it kind of phony. It's not really that high resolution. So you're better off getting rid of the zoom lens and making a nice sharp focus there, even if it only covers a fraction of the whole detector, than to put in the zoom lens. But you still see a lot of interferometers out there with these zoom lenses in here. Any questions on that? So back in my WICO days, when I was running WICO, we got sued for patent infringement. Maybe that's another reason why I don't like zoom lenses here. And we got sued for patent infringement for doing two things. One was putting in a rotating piece of ground glass and a zoom lens, and for aligning an interferometer by bringing these two spots together. So, I swear those are things I did in graduate school, long before the patent came along. But there was a patent, and it ended up in a 10-year lawsuit that I battled for bringing two spots together and using a rotating ground glass and a zoom lens. So that's probably another reason why I don't like zoom lenses anymore. Okay. So let's go on here. This is something near and dear to me right here. And I think at the last class, some of you mentioned this or asked questions about polarization beam splitters and so on. So often, instead of using just a flat plate here with some wedge in it, people will use a polarization beam splitter and a lot of other optics with it. And the idea works as the following. Let's say we have a laser here, and let's say the light coming out laser has linear polarization, and I show it here at 45 degrees, but we may change that in a minute. But right now, say at 45 degrees. We come along here to a polarization beam splitter that will reflect one polarization, and I guess I say the S, and it will transmit the orthogonal polarization, the P. And the light goes out here to my reference and comes back, and out here to my test and comes back. Now I want to take the light out here. It's possible that I could take the light going back here, but for this drawing I'm going to take the light down here. And so what was reflected the first time, the state of polarization reflected the first time, I'd like to have it transmitted the second time. And what was transmitted the first time, I'd like to have it reflected the second time. And so we use a well-known trick of a quarter wave plate at 45 degrees, a little bit like the optical isolator here. Quarter wave plate at 45 degrees. And we go through it twice, so it acts like a half wave plate. And it's at 45 degrees, so it's going to rotate the direction of polarization 90 degrees. And so what was reflected will be transmitted, and what was transmitted will be reflected. So we don't have light going back here. That's kind of nice. No light The light's not going back to the laser. So that's a nice thing about it. So the two beams coming out of here, the test and reference beams, have orthogonal polarization. And so what do we see for the interference right after the beam splitter? Two beams have orthogonal polarization, so we don't see any interference, okay? So we put in a polarizer here, and I'll put it in at 45 degrees right now. And lo and behold, down here we're going to see interference. Okay. And so it's pretty nice. So we didn't have any light going back towards the laser anymore. So we don't have to worry about that. And all the light that went in here is coming out down here. That's nice. Now let's say I adjust this just right to get one interference fringe here. And let's say it's a dark interference fringe. Where has the light gone? Someone needs to help me here. I forget. Where's it gone? What? Ah, yes. It's gone in the polarizer. Whatever the polarizer does, maybe depending on the type of polarizer, it may absorb it, it may reflect it. In fact, what I could do here, I could put in another polarization beam splitter right in there and orient it just right. I want to orient it at 45 degrees. And I could get an output here and an output here, and I would see that these two outputs are complements of one another. So isn't that kind of neat? Okay. Well, this, we use this a lot at our company, 4D Technology. Almost every interferometer we make has this in it, because we'll make use of the light coming out here, the two beams having orthogonal polarization. But there's some other nice things about this. Let's say the reference mirror. Well, let me go back here. If down here, let's say I'm testing something 100% reflectivity or very high reflectivity, then I want the reference mirror to be very high reflectivity. Because we saw last class that changing the reflectivity of the beam splitter doesn't change the relative intensities of the two beams. And so I want, if this has a high reflectivity, I want this to be a high reflectivity. If this has a low reflectivity, then I want this to be a low reflectivity. If I come here, and let's say, I have a high reflectivity here, and I have a high reflectivity reference surface there. Now let's say I want to test a low reflectivity surface here. How could I match the intensities of the two beams? Can you give me two ways of doing it? Yes?
Orient the polarizer at the output where the test and reference both pass at a different angle.
That's right, very good. So I could just rotate this to match the intensities of the two beams. How else could I do it? Well, I could change the direction of polarization of light going in. And sometimes what people do is they put a half wave plate here, and you rotate the angle of the half wave plate, and then that will change the angle of polarization, so that will change how much light goes into the two arms. Which way is better? It's not going to be a huge difference maybe. Which way is better? Rotating the polarizer here or rotating a half wave plate back here? What? Input? Why? You're right, but why? Oh, well, it's more efficient. If if I'm rotating this down here, I'm going to be throwing away some of the light to match the two. Up here, I'm just changing the direction of polarization to match the two, and I'm not throwing away light. So this is a little better to rotate the half-wave plate here than to rotate this polarizer, but they're both pretty good. Okay. So this is, I mean, this is great. Why don't everyone do that? Why do we even have the other approach? Why wouldn't you always do this? What's wrong with it?
Birefringence.
What?
Birefringence.
Oh, that could be a problem. You could be testing something that has birefringence that could mess you up. I haven't had a lot of trouble with that, but that certainly can happen for sure. Depends what you're testing. Well, I think academically this is great, but if you're making an instrument, I have to buy a lot of optics. You know, it costs a lot of money. You have so many optical components. And you have so many places where you can get errors. And it's hard, it's expensive to get all of these optics here and still have high quality. You can do it. I mean, we do it every day at 4D. But you end up spending a lot of money. But there are some really great things that we'll see later in the course that you can do when you have the two beams coming out here have orthogonal polarization. But, I mean, it's a very efficient way, light efficiency. It's just that you end up buying a lot of optics, spending a lot of money. So we're going to see this, I don't know how many times in the future in this course, many times. So I want to make sure that you completely understand it, because I probably don't want to explain it again. We're just going to see it in a drawing, and I'm going to say, we've explained that before. So any questions at this point? Okay. Well, I love it. So. Okay, so now, I mean, we're so good at testing flats now. But now I want to test a sphere. And if I go back, well, I could do it right here, I guess. If I put in a spherical surface here, I'm probably going to get too many fringes down here. Just not going to work. And so how can I test a sphere? Well, the idea, it's okay if it's complete garbage on my computer. Let me come back. And now it's okay. I don't know. Sometimes I think PowerPoint has a mind of its own. Anyway, now I want to test a sphere. So if we stick with the Twyman green here, all I'm going to have to do is to put in a lens here, producing a spherical wave. And if I put this in, so this is right at the center of curvature of this mirror, if this is a spherical mirror, the light will go down here, the rays will be normal to the mirror, and they're going to come right back on themselves. Come back here, going to be collimated. So once again, I'm interfering two collimated beams, just like for testing a flat. So isn't that neat? So the procedure I would do, I'd put in this lens. I'd put a little card here with a hole in it to get the light going through the card. I'd come back here, and I would move this back and forth and tip and tilt it to bring the light back through the card. Okay, so now the light's coming back here. And so now I'm going to see these two spots. Okay, and I'm going to bring it to focus here, not worrying about infringing a patent. I'll bring these two spots to focus here. The patent's expired now anyway. Bring the two spots to focus here. And then I'll tip and tilt this, really just superimpose them, and I'll see fringes down here. And they're probably not going to be straight. They're probably going to be curved a little bit. So then I will change this spacing a little bit, either by moving this mirror, or more often you just move this lens a short distance. So you get the beam coming back as collimated as possible, and you get fringes as straight as possible. And that's it. So isn't that neat? I mean, it's nothing new here. Twyman and Green did this in 1916, and probably people did it before then. And then, if I have a different radius of curvature, say a concave mirror, different radius of curvature, I just move it back and forth here, so the center of curvature is always at the focus here. Pretty simple. Okay. If I have what diameters could I measure here? This might be, say, a centimeter. How large could this mirror be? Could we go over to the mirror lab and get one 8.4 meters in diameter? Would that work? Even though this is only a centimeter here? Of course, the answer is yes. You just have to have this lens so this cone angle here is large enough to fill the mirror when the mirror is situated such that the center of curvature is at the focus here. Okay. So that's really nice. I just move this back and forth just so the center of curvature is always there. Test almost any size concave mirror I want. What if I want to test a convex mirror? What do I do now? Well, I put it in here, so the center of curvature is there. Now, what diameter and radius of curvature convex mirror can I test? Well, here we have the problem. It has to fit in this space here. And so we're limited both on diameter and radius of curvature for convex. Concave is nice. Convex is always a little more difficult. Okay. So now your boss comes along and he bought this interferometer for you for $100,000 or something, and now he wants to test a lens. How are you going to test a lens? Well, I'm really testing the lens and the mirror together. Right? And when I was testing that mirror, I was kind of assuming that was a good lens. Later in the course, we'll find ways that we can calibrate out errors in that lens. But right now, if I really want to do a good test of a mirror, I want to have a good lens there. But if I want to test a lens, well, all I need is a good mirror. And it could be a concave mirror, or it could be a convex mirror. I don't care. But I'll just test this, and if I know the mirror's good, then whatever error I'm measuring is coming from the lens. Okay. Well, unfortunately, I find I don't have a good concave or convex mirror. So why not just put in a little flat mirror, put in a mirror right there? I mean, the light's focused right on it. So the light would come down here and hit that mirror and go right back and be collimated. So wouldn't that be a good way to test that lens? No. Why? What's wrong? What? Well, you cancel the odd ones, yeah. The beam is flipping over, and so I'm not going to see odd aberrations. So like coma, I won't see. So what I always say, if you're selling optics, this is a very good way to test a lens. Just put a flat there, and you're not seeing the odd aberrations. But if you're buying optics, don't let them get away with that. That's not the way to test it. Okay. So let's see, what good optics do we have to have? I want to test mirrors. What that lens, I mean, unless I go through some calibration procedure, which we'll do later in the course, but typically that lens has to be good. That mirror has to be good. That beam splitter has to be good. And I think, like we said last class, the imaging lens doesn't have to be real good. And however, we're expanding the beam back here to get the collimated beam here. That beam expander doesn't have to be real good either. But we do have 3 pieces of optics here that have to be good. And the lens, the beam splitter, and the mirror. Yeah, a ball is actually pretty good. A ball bearing. A lot of ball bearings are actually pretty good quality. And so you could put the ball bearing in there. And so it's like a convex mirror. Sometimes they're rough, but a lot of them are pretty good. Pretty good. In fact, you go down, I've done this a few times. Go down to our machine shop downstairs, and there's a cabinet. I know it has a lot of ball bearings in it, so I'd go in and steal one of those to test something. It's pretty good. And, I mean, this imaging optics here, we want to image this, whatever we're testing here, we want to image it down here. So this lens is forming an image of that someplace back here, and then this is going to relay that image down here. If I'm testing a lens, well, things are a little bit more difficult because I'm going through the lens twice. And imaging is not quite so easy. So how many of you have used a Twyman green like this to test? Okay, good. That's really pretty neat, pretty neat. Now if we go back to the Twyman green days, 1916, they did this test. I mean, they have a patent on this, but it was more difficult then. And you didn't have as much freedom what radius of curvatures to measure. Because the problem then was that they didn't have a laser. And I mean, here I have quite a large path difference. And so I have to have coherence of that larger path difference. And so what they did, well, they would go to maybe a mercury source and filter it down, low pressure and not much light and everything. You know, and then they would also, you could move this reference mirror back here to equalize the paths. I mean, that's not so easy to do if this is a 10 or 20 meter radius of curvature. But over a certain range, you could match paths by doing this. But when the laser came along in the early 60s, I mean, this was wonderful. This was such a great thing to be able to test very large, long radius of curvatures with a setup like this without having to match the paths. And so some people, instead of calling this a Twyman green, they gave it a different name. And the name that they gave this interferometer was Loopy, L-U-P-I. Or Loopy stood for laser unequal length interferometer. So instead of Twyman green, I called it Loopy. Okay. And nowadays, people often would just use a single mode laser here. And so they don't, you know, they can have large path differences without any trouble. In the early days of using just a helium neon laser, I'm sure you've had this in 505, but I'll mention it here. Think of a helium neon laser, and if the cavity is more than, I don't know, 10 inches or so, you're going to get more than one longitudinal mode coming out. And so you have all these different frequencies. And so your coherence function is, what, a periodic function? And so if that's true, do you remember, so the round-trip path difference between these two arms should be close to, what, an even number of laser cavity lengths. Did you have that someplace in your past, 505 or someplace? And so if we go back to interferometers that were made in the loopies that were made in the 60s and 70s and maybe even the 80s, what they would do would be mount this mirror so I could move this one laser cavity length. And so regardless what radius of curvature here, I could tweak the cavity here so the path difference was close to an even number of laser cavity lengths. And so I could always get good contrast fringes. Nowadays, you kind of forget about that. You just go to a single mode, single frequency laser. You don't have to do the tuning here. So if I'm testing, 98% reflectivity mirror here, I put in a reference mirror up here, 98% reflectivity. If I'm testing a uncoated mirror here, 4% reflectivity, then I probably just put a reference mirror here that's 4% reflectivity. Or, I could go back and I could use this here. And so here's where I put my lens and my mirror I'm testing. And then I could match intensities by either rotating the polarizer or rotating a half-wave plate back here. But it's easy here to match the intensities of the two beams. Kind of a headache here is, again, you have this lens here, you're illuminating the lens, and you're getting a reflection off the lens. And even if you spend a lot of money for a good AR coating, you're probably still getting a little bit of a reflection here. And that's coming down here and giving you some fringes you don't want. But so that's a kind of a practical problem you run into. Okay. Any questions on this? So this is, well, I'm going to say this is my favorite interferometer, but I know I'll say that about other interferometers. But right now, this is my favorite interferometer. It's so versatile. You can test almost anything with it. Okay. And later, we're saying these optics have to be good. Later, we'll talk about ways of removing the errors in the software. Next slide shows this is just an interferogram taken with one of these Toyma-Green interferometers. Hate to think how many times I've published this picture in different papers, but it's just a typical interferogram. And you can certainly see we had some errors present. And pretty good contrast fringes. Looks pretty nice. Okay, so this is a great interferometer. The problems being you have 3 optics here. The main problem being you have 3 optics. You generally want pretty good quality. And so it might raise the cost a little bit. So how can we get around that additional having to have so many good optics? And that takes us back to the Fizeau. The Fizeau required only one high-quality reference surface. We had some problems with the Fizeau, as described before, in that we put the 2 pieces together, and so it's easy to scratch one of the surfaces. And for every different radius of curvature we tested, we had to have a different radius of curvature reference. We can get around that by using a laser source. So when the laser became available, people began making laser-based Fizeau interferometers. And so if I'm testing a flat here, Well, I mean, it's really just like with the old Frisell. I'm going to illuminate this, but I'm going to use collimated light here. And this is going to be what they often call transmission flat, just a reference surface. And so we're going to look at the light reflected off the second surface here, and the light reflected off the test. So it's just like the Frisell, except now I have a laser, so I have more coherence length, so I don't have to put these two surfaces so close together, and so I don't have to worry about scratching so much. And so what optics have to be good? Well, I mean, certainly the beam expander doesn't have to be high quality. The beam splitter here, does that have to be high quality? No. The first surface here, high quality? No. Second surface? Yes. And of course, this is what we're testing. And the light goes back here. Imaging lens, not high quality. Back here to interferogram. So we're back to only requiring one high quality surface here. We will probably, in this transmission flat, we'll probably put some wedge, because I have another surface here. I have to watch out for reflection off of it. So we'll put some wedge here, and maybe a cheap AR coating on it. So at least we can tell which, when we look at the beams reflected off two surfaces, we can tell which came from which surface, because one would be brighter than the other one. And again, we just bring our two spots together down here. And the spot coming from the reflection off the other surface will be dimmer, and that'll be off to the side. So it won't get to the interferogram. Maybe that's all I'll say about this right now. Oh, well, the beam here, I mean, how good does it have to be? We think here, again, we have some path difference between the two beams, so it can't be completely garbage, but just going back to 505, we know that the path difference will go as 2d cosine theta, d being the distance here, and theta is the angle of the beam inside. And so we don't want to have the error so large, but what 2d cosine theta introduces a sizable amount of error in the measurement here. Typically, it's not going to. These distances typically are not very large. Few, 2, 3, 4 centimeters typically. If I want to test a curved surface, I can't just put it there because I'll get too many fringes, but we'll go to this version of the Frisell, where now what we do here, we put in a lens. It's going to bring the light to focus here. And just like before, we're going to put that at the center of curvature of this mirror. And then we're going to be very clever when we make this lens. We're going to make it so the beam leaving the lens is normal to the last surface. And so that last surface will be the reference surface. So we'll look at the light reflected off this surface and a light here, and that will tell us errors in this mirror. And so, again, beam expander, beam splitter don't have to be high quality. Imaging lens is not high quality. And even this lens now is not high quality except for the last surface. Okay. So before the laser came along, this was not a very good setup, because we just have a large path difference. There's no way of getting around it. Path difference equal to twice whatever the radius of curvature of this is plus this distance here. And so this was not a practical system until the laser came along. And then even then, when the laser first came out, you didn't, you didn't have a way of tuning the path difference between the two beams like you have with a Twyman green. So right at the beginning, you had to go to a single mode laser, which for the early days meant you didn't have a lot of light. It's not such a problem nowadays, but you didn't have a lot of light in the early days. So this has become probably the most common way of testing spheres, because you don't have to have so many high quality optics. It's only one surface that has to be high quality. Any questions? Well, okay, let's say, this has some reflectivity here. And typically they use an uncoated, common anyway, to have that uncoated. So that'd be a 4% reflectivity. And so if this is a 4% reflectivity, you're okay. The two beams have the same amount of light, and you get good contrast fringes. But if I'm testing something here with a high reflectivity, say 97%, and I get 4% from here, how do I match the intensities of the two beams? Typically, there are two ways that people use to match the intensities. The first way is that we put in some type of attenuator here. That, if we get 4% from there and we get 90-some% from here, I want this to be such that when the light goes through here twice, you get 4% back. Okay? So you put in some attenuator. Now this is a spherical beam, and so if this is a plane parallel plate of some thickness here, we get spherical aberration. When we tilt it, we get coma and stigmatism and so on. So this cannot be very thick. Okay? It has to be thin. So we have to use something like a pellicle. Now the other day when we're talking about beam splitters, someone suggested using a pellicle for a beam splitter, and I said no, because it's going to vibrate, and it's going to act like a drum, and fringes are going to jump around. But here we're using it in transmission, so it doesn't matter so much that that the thing vibrates. And so a very thin pellicle works well here. Now there's one thing wrong with a thin pellicle, and of course none of you people here would ever have this problem, but it's very easy to stick your finger through that pellicle. Has anyone here ever done that? What? First person I ever met in my life who's done it. Someone back there too. Two people. What? No, you can't clean them. If you clean them, you buy a new one. Yeah. So back when I was running Wyco, we sold a lot of pellicles. This was great. This is a great sort of, a great thing to sell. But I don't find people who admit that they stuck their finger through it. It's more often, I went home at night, the pellicle was fine. I came in the morning and it was broken. I don't know, I think it's ghosts again doing it. But yeah, that thing is very easy. It doesn't take much to destroy that pellicle. What? Yeah. So another approach that people use is they'll put a coating on here that absorbs some of the light going through, and so they get about 4% back. Okay. Now, a problem here, this is not a very light efficient system. We're getting 4% back from here, and in some way I always make it so we get about 4% back from here. And so we're throwing away 96% of our light. So that's maybe a little negative thing about the laser-based Fizeau. Okay. So, back in the days, at the same time that I was sued for patent infringement of putting two spots together and using a moving piece of ground glass, I also got sued for using a pellicle here. And I was completely innocent in this. Not because I wanted to be, because I wanted to use a pellicle there, but there was no patent on using a pellicle here in a collimated beam. But I knew there was a patent on using a pellicle here. And I wanted to infringe that, but I didn't. But I got sued for it anyway. They later dropped that suit. But in looking at their patent, it was very easy to invent around the patent, because they had made this patent so restrictive that they were getting rid of light by absorbing it in the pellicle. But, I mean, the other way to get rid of light is to put a coating on it, reflect it away, and then just tip this a little bit. And so we did that and got a patent on that. Okay. Okay, I guess maybe that's everything here. Trying to think. Okay, I think it's time to give you a quiz. Of course, some of you have the notes in front of you, so you're going to cheat probably. So those who have notes in front of you can't answer this question here. So we have this interferometer here, laser-based Fizeau, and we're testing this mirror. And when I test a mirror, I get fringes that look like this. So they're pretty straight right here. But over here they have a little wiggle. So is that a bump on the mirror? A hill, I guess I say here. A bump or a low spot, a valley? That corresponds to a bump, a hill, or a valley. Drink some coffee. In fact, maybe now's the time to talk about the football game, too. What do you think? How many of you went to the football game? No one. I tell you, you missed a heck of a game. That was the best U of A football game I've gone to in years.
To answer this question, you don't need to know which way.
Trying to avoid the fact they didn't go to football. Yes, right. I haven't given you enough information. So far, you can't answer that question. I haven't given you enough information. I'm going to give you one more piece of information, because you don't know what direction the wedge is. So, what I'm going to do is just push in on this mirror, just a little bit, not much. And I probably won't even, I might use my finger, but more likely I'll just use a card or something. I don't want to push on it much, just a little bit. And when I push in on this mirror, the fringes move this way. So now, now you have all the information you need. Well, I mean, it's the election year, so I think we'll have to vote again. Yes? This gives you the information about the tilt.
Oh, sorry.
Yeah. So maybe we'll vote. And some of you have answers there, so you're going to cheat probably. But how many say it's a hill? Raise your hand. 1, 2, 3, 4, 5, 6, 7, I guess. 8, 9, 10, 11. 11 hills. How many say it's a valley? 1, 2, 3, 4. 4 valleys. I don't know. That's 15. I see a lot more people than that out there, I guess. The rest of you are saying it's perfect. Is that right? Well, the democratic process worked. It is a hill. Now, those of you who said hill, how did you know it was a hill? Other than the fact maybe you looked in the notes. I'll tell you, my simple-minded way of thinking about this is that if I push in on this, it's like putting a bump or a hill over the whole surface. And when I put a bump or a hill over the whole surface, the fringes move towards the right. And so this little region here, where the fringes move towards the right, must be a little localized hill or bump. Okay. Pushing in made putting a bump on the whole surface. You don't push in very much, just barely touch it and the fringes move. Okay. Well, the other thing I always say, maybe I've already told you this, I can't remember, but this is if you're making optics, this is certainly critical. You want to know, is that a hill or is that a valley? And otherwise you may make the valley deeper. And nowadays, all the interferometers are computerized, and assuming they didn't mess up the software, whoever made the interferometer, it's going to tell you whether it's a hill or a valley. But it's still nice to know that, being able to check it yourself and not relying upon the computer being right, computer software being right. And what I always say, if you go out on the street and you ask people at random about this, half of them will get it right. But then I always think, and I've seen this, you go into a room filled with PhDs in optics, and you ask them this question, and they'll think about it and figure it out. About a third of them will get it right, seems like. I don't know. It's so easy to make a mistake here on this. And I've done it myself. I remember once years ago, and I gave an exam, and had a question, something like this on it, and I graded it wrong. And it was a midterm exam. I didn't realize I graded it wrong until I was making up the final exam. So we went half a semester, and not a student in the class complained about the fact I graded his exam wrong. So it's very easy to make a mistake here. Well, there are lots of interferometers, and I'll look at one more before we break today. And this is called a Mach-Zehnder interferometer. And it's used to measure samples in transmission. And nowadays you'd use a laser. In the early days you, of course, didn't have a laser, but now you'd probably use a laser. So you collimate the light, and the light goes around here and out, and it goes around here and out. And if we put a window in here, then I'm measuring that window in transmission. So I'm seeing optical path differences going through that window. And again, I would image that window right here. Let's say everything is perfect, and I get a black fringe right there. Where has my light gone? Very easy to see here. If this is a dielectric beam splitter, you'll see that this pattern up here is a complement of this. And just like before, if you have metallic coatings, then they're not necessarily complements. You have to take into account absorption by the coating. But this is a very nice interferometer for if you're using dielectric coatings to see the two outputs here are complements of one another. And you want to sit down and go through and look at the reflections here to convince yourself that these two patterns are 180 degrees out of phase. Now, I think in 505, you probably looked at the Mach-Zehnder some. Nice thing about the Mach-Zehnder is that, well, the paths are matched here. And so I don't have to use a laser source. The paths can be matched if I do this right. Furthermore, I don't even have to use a point source here. And I can I don't know if you saw this in 505, probably did. You know, by tipping and tilting different elements here, you can get the fringes localized. You can get the fringes localized any place you want. And it's fairly easy to get the fringes localized back here in the plane of the sample. And so when you image the sample, you see both an image of the sample and you'll see the fringes localized there. Of course, with a laser source, you don't care. The fringes are non-localized with a point source. So that's the Mach-Zehnder. So the next class, which as I said, I will record this afternoon at 2 o'clock, and you can either see it then or you can come to class on Thursday and see it. We'll go on and say a little bit more about the Mach-Zehnder. And I'm going to talk about some interferograms and moire patterns and so on. So I'll see you later. Old homework, if you haven't picked it up, it's up here.